Welcome to the course. To everyone who is courageous enough to come here so early. Today I want to talk about lazy evaluation, which is a very different way of computing, and if you have not seen it before, it will seem very weird and strange and powerful. Okay, first a few seconds for the Ukrainians who are still fighting for their freedom for ours. Okay, so I want to talk about lazy evaluation. I will start by showing you what it does. It's very easy to use. I'll give you an example. And then I will immediately give you the semantics. It's actually very easy to define in deterministic data flow. And after that, I'll start programming with it. I'll show you how to do producer-consumer. So the streams can be very powerful with lazy evaluation. You can also program with infinite data structures. I will show you how to do that. And then a very interesting example is the Hamming problem. It's a recursive stream problem using laziness. And if I have time, I'll talk more about how it's executing, really, we'll go in detail. And I combine it with concurrency. Because laziness is a very different thing from concurrency, and it's very interesting to combine laziness and concurrency. Okay, first I want to give you some introduction. What is lazy evaluation? It's just a functional program, like we saw before. Any functional program that we saw, you can run it lazy. And what does that mean? It means it executes by need. That means when you call a function, it does not execute the function. It just creates something called a lazy suspension, and it will only execute the function when something else needs the function. Okay, so that seems very weird. Okay, so let me give the semantics of lazy evaluation, and at the same time, it will give the semantics of the data flow execution. Okay, so how does lazy add work? So remember, we saw that the semantics of a program, you get it by translating into kernel language. Okay, and so I'll show you how the lazy add is translated into kernel language. So here's the translation. So lazy add, x, y, r is the result. And here's what it does. It creates a new thread, and in that thread, it waits. There is a special operation called wait needed, which will wait until r, the result, is needed. So the wait needed is a synchronization, and it will wait until another thread needs r. Okay? So what does that mean, to need r? Well, there is an operation called wait in the system, which will wait until r is bound. Okay? So the wait needed will wait until another thread does wait. So if I do wait needed, r, this one will wait until somebody needs the thread. But if there's another thread that needs r, the other thread will do a wait. Okay? So how does that work in the full system? I have to refresh your mind on how the data flow execution works. Okay? So let's say I want to do s is equal to x plus y. Okay, this addition operation adds two numbers. Okay, but remember we are running a data flow, deterministic data flow functional language, which means that the addition has to wait until x and y are numbers, because they might be unbound variables. So this is translated as follows. I'll show it here. I wait until x is bound. I wait until y is bound, and then I will actually do the add instruction. So there is some primitive add instruction that will only work for numbers. X plus y gives v, and then there is a bind operation which binds unbound variable. So this will bind s to v. Okay. So the v is a local variable. So this is how the data flow works. Whenever I do an addition, I wait until x and y are bound, then I do the actual addition instruction, primitive, which assumes that x and y are bound, and after that it binds v to the result, and then I have a special operation bind. Okay? So the semantics of this is wait x will suspend the current execution until x is bound to a value. Okay, and the bind operation will bind x to value v. So whenever I do a bind of x to some value, then the wait, if someone else is doing wait on x, the wait is going to continue. Okay? So this is always how the data flow works. So no matter what you're doing, every operation that you do will, if x and y are unbound, it will automatically wait. Okay? So that's part of the data flow execution. Okay? So wait and bind are used everywhere already in the system. Okay? So all operations that the programmer uses are defined using wait, bind, and a primitive one that doesn't wait. Okay? So the arithmetic, addition, subtraction, also the case statement. If I do case L of h bar t, this one will also wait until L is bound. If L is unbound, it just waits, and when some other thread binds L, then the case will continue. So remember, we already have done this. Huh? This is something that's already done in the previous course. Remember, I explained all the data flow in the previous course. So this is how the data flow is already working, the deterministic data flow, and it's always doing like that, okay? And even things like function call. If I do f of x, where f is a function, well, f might be unbound. So the function called f of x will wait until f is bound to the function. Or the record operation. R dot, the field name, R has to be bound to a record. So it will also wait, the dot operation. Okay? So this is how the data flow is already working, and it waits forever, right? There's no timeout or something like that. That just waits until another thread binds the value. And the lazy execution is just one more operation added to the data flow. So I have wait, and I have bind, and to do lazy execution, I have now a third operation, which is called wait needed. Okay? So the third operation, wait needed x, wait until another thread does wait x. So you see, this is a kind of funny, more sophisticated condition. Huh? The wait needed x will wait until another thread does wait x. The thread that does wait x, it does wait x because it needs the value. Okay? And so the wait needed is basically waiting until somebody needs the value. Okay? So that's how we add laziness. So there's just this one new operation, Be careful not to confuse wait and wait needed. Huh? Wait waits until x is bound to a value. But wait needed it doesn't wait until x is bound to a value. It waits until another thread does wait. Okay? So that's a little bit subtle, huh? So this third operation is what lets us do lazy evaluation. Okay, so that is the complete semantics. With that, you know everything about the data flow, but also how the laziness works. So there's nothing else. And I'm going to show you very clever programming techniques. We're going to do very neat things with laziness. And all the neat things is just using wait needed. There's nothing else. I'm not hiding anything. There's no other magic. The only magic is wait needed. Okay? So you can actually use wait needed directly in the system if you want to play around with it. For example, I can do wait needed x, and then after that I bind x. Okay? So for example, I can do something like this. I can say declare wait needed x, and then I bind x, for example, to 100. Okay. Now if I browse x, I just get an unbound variable, you see? Because the wait needed will be waiting, still waiting, because nobody has actually done wait. Okay. But now if I do browse x plus 0, you think it's doing nothing, huh? X plus 0. But the addition operation, the plus, has to use the first argument that has to be a number. So this one will wait. And it's doing wait. And that means the wait needed will continue, execute. So if I do browse x plus 0, then it will display 100. And the first browse, the first underscore variable will also be displayed. So you can see that this causes the computation to continue. Okay? So you see, this is a very interesting way of controlling the computation. Huh? Okay. So in general, in Oz, you can make lazy functions. You can say fun lazy, and then you have your function f with the arguments, and then it looks just like a regular function. Okay? But this will automatically be translated like this. It will be translated into a procedure. So here is the result R. I create a new thread, and in that thread, I wait until somebody needs the result. Okay? And when somebody needs the result, then I will do R equal expression. Then I will do the computation. So when I call the function f, I'm not executing immediately the function. I'm creating a thread that does wait needed. Okay? And that, I call that a lazy suspension. Okay? So the laziness happens exactly like this. There's no other magic. But you will see, this is already a very powerful magic, okay, as we will see in a little while. Note also, you might think this is kind of expensive. I'm actually creating a thread just for a function call. Yes, that is a bit expensive, but remember, the compiler doesn't have to do it this way. The compiler only has to respect the semantics of this. So there are many, much more efficient ways of implementing laziness that I won't talk about, and there's programming languages that are based on laziness. So if you're interested, you should take a look at a programming language called Haskell. which is completely based on lazy evaluation. All functions are lazy by default, and still it's very efficient. There's a very efficient compiler for this. So Haskell actually has a large user community, and it's based on lazy evaluation. Okay. So I'm not going to talk about Haskell today, but if you're interested, you can look at that. And so you see, this is how all functions are translated. Okay. So that's the semantics. So now, basically, you know how it works. But now I'm going to run programs. So the rest of the lecture, I'm going to show what you can do with this idea. Okay. And the first example will be producer-consumer example, and I will use streams for that. And then I will show you different versions of it: sequential, concurrent, and lazy. Okay? 3 kinds of producer-consumer. Okay? So I'm going to give the code of a simple producer-consumer. So the producer will create a stream which is sent to the consumer. So here is the advantage, the code of it. Producer will go from L to H. So it basically creates a list, L plus 1 up to H. So I give it an end, or otherwise it's an infinite loop. But as we'll see later on, in a lazy program, you don't have to give it an end. But here I'm also executing it non-lazy. So I will wait for 1,000 milliseconds, so I'm slowing it down, and here I'm creating the list. So L followed by producer L plus 1 H, and I end with nil. Okay, so that's the producer. And the consumer, to make it do some work, it's going to create the cumulative sum of all the elements that it has seen, and it will output that as a new string. Okay, so the consumer has an accumulator, and it will take the string S, and it will do accumulator plus H, which is the first element, and then it follows that by a recursive call. So basically, it's creating a list of accumulative sums. So if I have the list 1, 2, 3 here, and if the accumulator starts with 0, then it will do something like this: 1, 3, 6. It'll do 1, then 1 plus 2, 1 plus 2 plus 3, and so on. Okay? And I will execute it in 3 different ways. 3 ways, which are different executions: sequential, concurrent, and lazy. And all 3 ways will give me the same result. So technically, this is just using the Church-Rosser theorem. So this is something we saw in the previous course. It means that if you have a functional program and you execute it, well, any functional program can be written as a lambda expression, which we saw before. So I'm not going to go into lambda calculus, but I just want to explain to you the foundation. So any functional program that we do here can be written as a lambda expression. And the interesting thing about lambda expressions is that you can execute them in many different ways. You can do reductions in many different ways, but they all give the same result. That's a very powerful property of lambda calculus, and this is also called confluence. It means that if the execution is doing different thing, then they will eventually come back and give the same result. So it's said that it's confluent. Okay? So that's the theoretical reason for this. And so lazy evaluation is just another way of reducing a lambda expression. So it's nothing outside of lambda. It's just another way of reducing the same lambda expression. Okay? So let me write some code now. So I'm going to show you this example. So I'm going to show this example completely because it's important that you understand it. Producer, consumer. So
prod from L to H. If L is greater than H, then nil. Else L followed by prod L plus 1 H. Okay. Oh, let me put the delay there. Okay, so this is a producer. This will create a list of elements from L to H. So for example, if I do prod 1, 4, this will, after 4 seconds, create the list 1, 2, 3, 4. Okay. Let me make this a little bit bigger. Okay. 1, 2, 3, 4. So that's the producer. Let me now write the consumer here. So this one will take a stream and it has an accumulator. Okay. Case S of H bar T. Then it will do the accumulator plus H, and it will follow that by the consumer of T and accumulator plus H. So that's the new accumulator. Okay? And otherwise, if it's nil, it will just end with nil. Okay? So let me show you an example. So if I give the list 1, 2, 3, 4 here, and the accumulator is 0, it will give me 1, 3, 6, 10. Okay? So this is a simple producing a list and reading a list. Okay, good. Now let me show you how we're going to do this as a string. The first one will be a sequential execution. So I will do 3 executions. Huh? The first one will be just sequential. The second one will be concurrent, but not lazy, which I call eager. Eager is the opposite of lazy. So everything that we did so far is eager. Eager means whenever you call the function, it immediately evaluates. It's eager, okay? And the other one will be concurrent, but also lazy, which means that it's the same program, but the functions are lazy, okay? So here is a program. Browse S1, browse S2, S1 is equal to prod 110, and S2 is consumer S1 0. So how is this going to execute? So the first example will be sequential. So I have 2 strings. So I have a browse S1, which will be unbound. Browse S2. And then I will do S1 equal prod 110. S2 is equal to consumer of S1 starting with 0. So how is this going to execute? When I execute this, it will first display 2 unbound variables. S1 is 2. And then I will run the producer. But remember, the producer has this delay in there, okay? This delay here. That means this producer is going to take 10 seconds. This call here will take 10 seconds. So during the 10 seconds here, nothing is displayed, nothing. So I'm waiting 10 seconds, and after the 10 seconds, the producer returns, and it displays the result, 1, 2, 3, up to 10, boom. And the consumer can then run and show its result. Okay, so let me run this. So, 1, 2, 3, 4, it's actually, why is it showing it? It shouldn't. Okay, I'm not sure what's going on there. The consumer
Okay, so the producer, now I'm perplexed. Why did the producer show the result incrementally? It shouldn't have. Okay.
I don't see why it shouldn't.
Because when I call the function, it only returns a value at the end when it's completely done. So it's basically binding it incrementally. Okay, so basically it's binding the result. Ah, okay. So I'm sorry, I'm confused here. I didn't expect the producer to give all this. But you can see the consumer waited until the producer was completely done. No? So the producer is basically binding the output while it's executing. Okay, that's something I didn't expect, even though it's not running in another thread. Okay, but you can see the consumer, boom, is everything all at once. So the consumer can only run when the producer is done. Okay, so basically the producer is binding incrementally the output, but the consumer will only run when the producer is completely done. Because here we have one thread. This is one thread. And while the producer is running, the thread is in here. And the consumer will only run when the thread finishes the producer and comes down to the consumer. Okay? So that's the sequential execution. So the consumer is doing a batch. Well, it seems the producer is binding its result incrementally. Okay. So this is something which I didn't expect. I'm not sure what's going on there, so I'll have to investigate that. But the consumer will only execute when the producer is done, because there's a single thread here. Right? So this is running one thread. So this producer, while it's running, it's also going to be binding the S, seems. But the consumer will only run when the producer is done, because there's a single thread here. That means the consumer, when it runs, it sees, it does everything, boom, at once. Okay? This is called batch execution. Okay? Now we do another version where we run the producer and the consumer in their own threads. Here we create two threads here. And it means that when we run this, the producer will be running in its own thread. So immediately we will run the consumer. Okay? The consumer does not have to wait until the producer is done, because the producer is running in its own thread, and the consumer will run also in its own thread right away. And the producer will be producing its output incrementally, and the consumer will wait and also produce its result incrementally. Okay? So instead of waiting 10 seconds, the consumer will start producing results right away, after 1 second. So let me do this version. So now the producer will go in its own thread. And put the consumer in its own thread. So the producer and the consumer, they are what we call agents. They are concurrent programs that take input streams, do computation. They might have output streams also. So when I run this, the output will come incrementally. So look carefully. So you can see the consumer output is being computed incrementally. So after 1 second, you already get a consumer output. Okay? See that? So the difference between the first version is, in the first version, the consumer will do nothing
for 10 seconds, and then pull everything at once. So that's a batch computation, whereas in the second case, the consumer is a concurrent agent. So as soon as the input comes, one by one, the consumer will already produce outputs. And that's because it's running in its own thread. Okay, so that's the second version. But now, what I want to show you is a third version, the lazy version. Okay, so I will make the producer and the consumer be lazy. So in order to do that, I will have to redefine them. I can't use the same definition. So I will redefine the producer to be lazy. So here. So I'm not changing the body or the code. I'm just making them lazy, lazy, lazy. But in order to have no confusion, I will call them L prod and L cons. Okay? So that they don't overwrite the previous ones. So I have a lazy producer and a lazy consumer. And now I will have the lazy version. So I have L prod, L cons. Okay? So I define the lazy producer and I find the lazy consumer. So remember how the lazy functions work. When I call the lazy function, it does not compute the result. Okay? It creates a lazy suspension. So basically, it will do wait needed. It will wait until the result is needed, and then it will compute the result. Okay? So you can see, this is the result of the lazy. It's exactly the same code, okay, except annotated lazy, and has two unknown variables. So it does nothing. Why is it doing nothing? Because the result is not needed. Okay? The result is not needed by anyone. So we have to need the result to make it work. How can we have to somehow need the result. So the browse does not need. Browse can display unbound variables, doesn't care. It doesn't have to display values. So one way to say we need the result is to ask explicitly for the first element of one of the results. So using a dot. So if I do S2.1, the dot operation will take the first element of this list, and the dot operation will need that. So the dot operation is doing a wait in the data flow. And so what that means is that it will force the lazy consumer to execute. So the lazy consumer here, S2.1. So when I do S2.1, it will force this one to execute. But this one is also doing a case. And the S here is the S1. So when I execute the body of the lazy consumer, it's doing a case statement on S1, so it will need the first element of S1. And that will force the producer to execute. So you see, I ask for the first element of the result. This forces consumer to execute, and the consumer needs S1, so it will force the producer to execute. So the need is going upstream. It's going to the earlier and earlier things. So the producer will then run, create one element. So you can see when I run that, it will display 1. Okay? S2.1 is 1, and the producer and the consumer will each generate one element. And then they stop again.
They will not run everything, they stop after one. How come? It's because it's doing a recursive call here. So when the consumer runs this case statement, it does a recursive call, lconst t. So this one will only execute when I need it, but I don't need it yet, because I'm only needing the first element. I don't need the second element, okay? So if I want the second element, I have to need it again. So if I do browse s2.2.1 in the list, remember how lists are done, huh? So you have seen the refresher. So s2.2 goes one down, and the dot one gives me the first. So this is the second element. And now I will need the T, the recursive call there, okay? And so the consumer will be running again, and this will force the producer to run again, and they will each generate one element. And then they do the recursive call. So you can see, look what's happening here. The producer makes 1, 2. The consumer does 1, 3. Okay? And so the 3 is out. And then they stop again. You see that they're doing the minimum work, yeah? The producer and the consumer. They're doing just exactly what's needed and not more. Okay? So, it's quite different from the previous execution. Huh? This one is doing a lot less work, but it's only doing exactly what you need. Okay? Okay, so here is the same thing on the slide. So nothing is computed. But if you do browse s2.2.1, then this will cause 2 elements to be computed because I'm asking for the second element. And the reason is that the dot operation needs its argument, and this causes the function to execute. But once the function executes, it will do a recursive call, and the recursive call is also lazy. Yeah? That means it will also wait till the result is needed, which means that the system will do the minimum work. Okay? Okay. So that's the eager versus lazy example, and there's an interesting way to look at it. So if you compare the eager and the lazy stream, the eager stream, that's the normal execution. It's the producer that is generating elements, and it keeps generating until it stops. In the lazy stream, it's not the producer, it's the user, it's the consumer. The one who needs the result is determining, is making the result be generated. Okay? So the termination in the first case is decided by the producer. It keeps producing elements until it's done. But in the lazy case, it's the consumer, or basically whoever needs it done. The final consumer determines when it's needed. So if this consumer needs nothing, then the producer will compute nothing. Okay? So the termination is decided by the consumer. Okay? So it's actually a symmetric situation. In the normal execution, everything is driven from left to right, producer to consumer, whereas in the lazy execution, it's going from right to left. So the need is coming from the right, from the consumer, and not from the producer. Okay? Okay. So that shows that we can actually go farther now. We can actually compute with infinite lists. The producer can actually be an infinite loop in this way of running. Okay? With lazy evaluation, we can compute with infinite loops. We can write programs with infinite lists. Okay? And it works because the producer will only produce what you need. So you will only be computing part of the the infinite list. So if we have an infinite list of integer, ints n followed by ints n plus 1. So that's an infinite loop, but this is a lazy function. So if we call ints 1, we have an unbound variable. So it's not actually doing an infinite loop. So let me show you how that runs. It has to be lazy, otherwise it will be an infinite loop. If you forget the lazy, it will be an infinite loop, and it will blow up the memory, and your emulator will crash. Okay? So if I forget lazy here, and if I call ints, it will create a list that grows very, very fast, and it will crash the emulator. So you should don't forget the lazy annotation. Okay, so I do this. So this now is something you cannot do in eager. So we are doing something now you cannot do in eager. In the previous example, where the producer went from L to H, we showed different ways of doing it. But now I'm showing you something that can only be done as lazy, because it's an infinite loop. So L is equal to ints 1, browse L. Okay, so I define this, I compile the lazy function, ints, and I call it, and it's just creating an unbound variable. So nothing is computed, okay, and the reason is that it's doing the weight needed. It only computes when we need the element. So if I want an element, for example, I do like this. So this is L.2.2.2.1. Okay, dot 1 is the first element, 2.1 is the second element. So this is the second element. Third, this will be the fourth element that I'm asking for. So I'm asking now for the fourth element. So how does this work? Well, the L.2 here, the dot will need L, and this causes ints to run. Okay? And the ints will run, and the recursive call will again stop. But the recursive call then, the result is L.2 is doing a second dot 2, and so the recursive call will be activated. And this will happen 3 times until we get the fourth element. And then it will stop because I'm not asking for more. Okay? So if we do that, we get 1, 2, 3, 4 underscore, and we display 4, which is the fourth element. And then the computation stops again. Okay? So you see how it's working, huh? It's only computing what we needed. So it's not a problem that it's an infinite loop. Okay, so you can see, so here's a translation into kernel language. It's very important because you can forget the translation and just program lazy, and eventually you kind of think it's magic or whatever, but it's not, okay? It's doing this. So the ints function is translated like this. It creates a thread, it waits on the result R, and then it does the recursive call. So when we do browse R.1, this causes R to be needed, and this causes this expression to be executed. N bar ints n plus 1. So R will be bound to n bar ints n plus 1. So this causes one element of R to be known, to be computed. And then we have the recursive call, but the recursive call will immediately suspend again, because every recursive call will do this. Okay? So that means if I do browse R.1,
I will execute the body, and then the recursive call will suspend again. See that, huh? Okay, so maybe I want to make maybe I need lots of results, and you can see by default, when I run a lazy program, it shows nothing. Okay, so nothing is not very much. So I can define a kind of helper function to force me to see the first n elements. So here's a funny procedure called touch. Touch, like touching the list. Touch ln. It says I need n elements of the list. So if n is 0, then I do nothing, so skip. And then I will do touch L.2 n minus 1. And I keep going until I've touched n elements. So this is a strange procedure. It doesn't do anything, okay? It only traverses n elements of the list. But this is enough for a lazy program. The L.2 will need L, so it will cause the lazy suspension to wake up. And then in the recursive call, I keep going on that for n steps, okay? So with the touch function, I can force part of the results to be evaluated, okay? You see, this is a very strange procedure. In an eager program, it doesn't do anything, okay? It's kind of very weird. But in a lazy program, it's very useful because it tells us that we need some of the results, okay? So let me show you how it works. Touch list, so I need n elements. So if L is equal to n is equal to 0, then I do nothing. Remember, there's a skip instruction which does nothing. L.2 n minus 1. Okay? So this is a very, very simple function. Procedure, sorry. Okay? Okay, touch. Now, let me try and run it. So we have already the L from before, the ints 1. We have this L here, the ints 1. So let me say I need 10 elements of this. And then we have 10 elements, 1 to 10. Okay? Then maybe we need 20 elements. Okay? And then we get 20 elements. And then it stops. Okay? So you see the touch lets you show part of the computation, but only n elements, and then it stops. Okay? Okay, so so now you see already the kinds of things you can do with lazy execution. You can, first of all, you can make things incremental. Sorry, you can make things, by need. So the eager was incremental. This one is batch. And this one is by need. That it only computes what you need. That's one thing. But the second thing is you can also compute with infinite data structures. They're not actually infinite, they're unbounded, potentially infinite, and you will only compute the part that you need, okay? Okay, so that's very simple. Now I want to go into another example, which is called the Hammond problem, where I'm going to solve a complicated programming problem, which if you don't use laziness is very complicated, but with laziness it's very easy. Okay, so this is called the Hammond problem. So first let's take a break. So now I want to show you a real example of a program that's easy to solve with laziness, but very hard if you don't have laziness. Okay? So this is a kind of problem. It's a recursive list problem. So this is called the Hammond problem. And so, because there's a guy, Richard Hamming, who introduced it. So I have to say a few words about Richard Hamming, because he was an amazing character. So he lived from 1915 to 1908. He worked at Bell Labs, and he invented many interesting things. So the guy was an engineer, but also kind of a mathematician. So he was always thinking. So probably you have already seen Hamming stuff somewhere. A Hamming window in signal processing, Hamming distance, maybe you've heard of that. Maybe you've heard of Hamming codes, okay, which are used sometimes to send information to space, to probes in far deep space, because they're very efficient, okay, and redundant. So this problem is also due to Hamming. And then I have to mention there's a very good book called The Art of Doing Science and Engineering, Learning to Learn. This is Hamming, when he was very old, kind of takes all his intuition and ideas and puts it in this book. So if you're interested, if you're kind of a curious, want to learn many things, I can highly recommend this book. Okay. So I have to say that when I talk about Hamming, okay? But today let's talk about the Hamming problem. So it's a problem of number sequences. And it's a dynamic problem, so we do not know in advance how much we need to compute. You see, we have to compute a number sequence, but we don't know how much we need to compute. So we have to keep going until we have everything we need. So that's a perfect kind of problem for lazy evaluation. Okay? So with lazy evaluation, the program is very simple, really, really simple. But if you try to run it in a non-lazy system, it's much more complicated because you have to manage all the neat stuff yourself. Okay? So let me explain the problem, and then I'll show you how to solve it using lazy evaluation. Okay? So the problem is very easy. It's kind of a mathematical problem. So we have a set of numbers of the form 2 to the A, 3 to the B, 5 to the C. So A, B, and C are integers. Okay? And so these are numbers that are products of the first 3 primes, 2, 3, 5. And you want to compute them in decreasing order. So you have 2 to the A, 3 to the B, 5 to the C. And A, B, and C are integers that are starting from 0. Okay? So we don't know how many numbers we need. We don't know in advance how many numbers we will need. We want to make the sequence. So the first number is 1, okay, clearly. The second one will be 2. The third one will be 3. The fourth one will be 2 squared, 4. The fifth one will be 5. Then we have 6, which is 2 times 3. 7 is not in the sequence. Then we have 8, 9, 10. Then we have 12, and it goes on. So there you see there's gaps, 7, 11. And the farther you go, the more gaps there's going to be. And we don't know how far. So we need to go up to a certain limit, but we don't know how many elements there are. So let's say I need to go up to 1,000. So how many of those numbers are there? I don't really know, okay? Because there's gaps. So I have to go up to a certain number, but I don't know in advance. And I want to generate the sequence as far as I want to, and I will decide when I'm generating it, how far I go. See, it's very dynamic problem, huh? Very, very dynamic. Okay, so how do we do it? So here's an idea. So we're going to invent an algorithm for this. Okay? And then we will implement it using a lazy program. So we have the sequence, let's call it H. H here.
which is a string, okay? 1, 2, it starts like this. 1, 2, 3, and it keeps going. Okay? Let's say we have these 3 elements. So the question is, what is the next element? So I write X, I'm writing an X there. So how do we determine this element? Well, intuitively, logically, this element is going to be either 2 times one of the previous ones, or 3 times one of the previous ones, or 5 times one of the previous ones. It depends, huh? Because the element will be A, B, and C. One of these numbers will be 1 more. So it's either 2 times a previous, 3 times the previous, or 5 times the previous. But we don't know which one, because it's the first one. So it's going to be the least number, which is like that. So the way we do it, so let's calculate the 3 possibilities, 2H, 3H, and 5H. So 2H will be 2, 4, 6, and so on. So only with the elements we know, 2, 4, 6. 3H starts 3, 6, 9. And 5H it starts 5, 10, 15. Okay? So this number is bigger than 3. Okay? So let me get a color crayon. It's bigger than 3. So here is the first number bigger than 3 in 2H. Here, the first number bigger than 3 in 3H. And the first number bigger than 3 in 5H. So this number, it will be one of these 3 numbers. Okay? But it'll be the least of these 3. So it's the minimum of the 3 possible next numbers. 4, 6, 5. Okay? And so the minimum will be 4. Okay? Okay, so that's good. So it's 4. But then we can keep going. Okay? So let's try now the next number. We can take a green shot. So we put 4 here. So what is this, the green number now? Well, it'll be the minimum number bigger than 4. So it's either 6, or 6, or 5. So again, we can compute it from the previous list. So it'll be the minimum of 6, 6, 5. So it's going to be 5. Okay? And then we advance. So you see, there's like a frontier here. Each time we take the first number that is bigger than the previous numbers in these 3 lists, and we pick the minimum. And then we advance like that. Okay? So that's our algorithm. Okay? We take the 3 sequences, 2H, 3H, and 5H. Okay? And so we have now a string problem. We have H is the string we want to compute, and we can compute it as a function of 2H, 3H, and 5H. So it's a kind of recursive equation, okay? H will be, the next element of H will be determined from 2H, 3H, and 5H. Yeah?
Is that possible to take 2 times the same number?
No. So
Okay.
each number occurs only once. So when we get to 6, the 6 occurs twice, but we only put a single 6. So the numbers, of course, are not repeated. Huh?
Okay.
We want all the unique numbers that are like this shape. So sometimes we have 2 of the same, well then both of them will advance. So,
Okay.
yeah.
Thank you.
Okay. So we're going to write a program to do this. And so we will compute H as a function of H. So there's 2 operations we need. So one is multiply the list elements by an integer, like by 2, 3, or 5. And the other one is merging 2 lists. So basically, I will take 2H, 3H, and 5H, and I will merge them. So the merging will always take the smallest elements. Okay? So L1 and L2 here
are in increasing order. L1 and L2 could be 2H and 3H. And I'm going to merge them in increasing order. So we'll start by taking 2, and then 3, and then 4, and then 6, and then 8, which is here, and then 9, and so on. Okay. But of course we have 3 lists, so this is a merge with 2 arguments. Okay? So this is the program now. This is the whole full program of the Hamming problem. So we have 2 functions, times, which takes a string and multiplies all elements by n, and merge, which merges 2 strings, so 2 ordered strings, and it generates 1 ordered string in increasing order. And then h, it's very easy to compute h. H is equal to 1, followed by merging the 3 times h2 times h3 and times h5. So we will call the merge function twice. Okay? Notice I'm defining merge with only 2 arguments. You could define a merge with 3 arguments. It would be more complicated. But so I want to keep it simple. So it's okay to have a merge with 2 arguments because we merge 2 streams and then we merge the 3rd one. So basically the final result will be the elements in increasing order. Okay? No repeat. So you see how the merge works here. I will take S1 or S2, so I have a pair. I will take H1 and H2, so the 2 elements of S1 and S2. If H1 is less than H2, then it starts with H1. If H1 is bigger than H2, it starts with H2. And if they're equal, then it also starts with H1. But you look at the recursive call. So if H1 is less than H2, then I will go 1. I will advance in the first list, but not in the second one. If H1 is bigger than S2, I will advance in the second, but not in the first. But if it's equal, I advance in both. And that answers the question that there's no repeat. Okay? If the same number occurs in both streams, I will go 1 step in both of them, because the number only occurs once. Okay? So that's the whole program. And times and merge are lazy. Notice there is no termination. These programs the program is basically an infinite loop. Okay? If times and merge were not lazy, this thing would execute and would very quickly expand, the list would grow forever and fill memory and the system would crash. Okay? Let me show you the execution of this. So let me declare first times. So this takes a string and multiplies all elements by n. So h times n followed by times tn. And notice there's no nil case here. It's going forever. In a lazy program, we don't have to care about termination. Okay? So merge S1, S2. Sorry, it's a function. So now I need to take 1 element from each of the 2. So the first thing I do is I make a pair. So the easiest way to do S1, S bar is 2. And then I take 1 element from S1. So the pattern is just a little bit more complicated. So here I've taken H1 and H2. So if H1 is less than H2, then the result starts with H1, and the merge will advance in S1, but not in S2. Okay? And if H1 is greater than H2, then it's H2, which is the smallest, so it starts with H2. And so I don't advance in S1, but I do advance in S2. And the final case is if H1 is equal to H2, then I can start with one of them, doesn't matter which one, but I have to advance in both. So this is not the same merge as in a sort. So in merge sort, you also merge lists, but you can't, if the two elements appear, they both have to appear in the result for a sort, because you can't have elements disappearing. But this is a different merge. Here I want all the elements in increasing order, but each element only occurs once in the output. Okay, so hopefully I'm not making any bugs. So I define merge and times. And now I define the main program. So the Hamming list, the final Hamming stream, it starts with 1, and then we have 2, 4, 6, 3, 6, 9, 5, 10, 15. So the next element will be the smallest of these three. So it'll be 2. So we advance, and then it'll be the smallest of 5, 3, 4. So it'll be 3, and so on. So we start with a list with one element, and now I merge. So times H2, and then I have to merge the other two, times H3, times H5, and then I can browse H. Okay? So this is the whole program. So it fits, it's not very many lines of code. You see, it's very short. So when Hamming made this example, the code, if you have to explicitly manage all of the need stuff, of course the program will be much more complicated now. So hopefully my code is correct. So here we run this, and as usual, in a lazy program, so nothing is computed, it gives you one underscore. So now we need some elements. So I will use the touch procedure we defined before to force this to compute some elements. So for example, I want 5 elements. 1, 2, 3, 4, 5. Okay. And maybe I want 10 elements. And then it will compute 10. 6, 8, 9, 10, 12. Or maybe I want more elements. So you can see we can decide how many elements we want during the execution. We don't have to decide in advance. We don't have to allocate memory in advance to try to predict how much it will be. We can do it all at the end when we're executing, okay? So here I've asked for 20 elements, and you see it goes up to 36 now, 25, 27, 30, 32, 36. Or I can ask for more elements, as many as you want. And the memory it uses will only be the memory you need for the elements that you have decided. So 30 elements, it goes up to 80, you see? 50, 54, 60, 64. So you see the gaps get bigger and bigger as you go higher and higher up. So you can see this is actually a pretty easy program to write as a lazy program. So you can see the power of laziness a bit with this, So this is the whole program. So this program, in the execution, it's the only new concept is wait needed. You can see that it's a very powerful concept. With this concept, and with the lazy function defined using this concept, we can write very new and different kinds of programs that we could not write before. So this program is something you could not write if you have not lazy. It's much more complicated. You can cannot run this code. If you want to run this program in a non-lazy language, you have to tell it how far. You have to compute how far you go. But then, what happens if you need to go even farther? Well, then you're stuck. You have to compute another piece going farther, so it's very complicated. So if you want to see how complicated, you can try writing this non-lazy way, okay? Okay, so let me now take a step back and talk a little bit more about how this is executed, okay? So remember, I introduced wait needed, and I said everything is there, and now I start writing lazy code, but maybe you forget a little bit how this is actually running. So I think it's good to take a step back and to look exactly at how this program executes, okay? So let me try to show that. So in terms of lazy suspensions. So let me try, now I want to investigate exactly how this program is executing. So it's fairly a bit complicated, huh? The merge function. So when I need a second element of H, it will activate merge. So we'll execute merge. But merge needs times and another merge. And then the second merge needs both times. So there's kind of upstream activation, okay? So I think it's interesting to look at that, to give you a stronger intuition really in how this program is executed, okay? So this is in terms of lazy suspensions. Okay? Okay, so we defined lazy evaluation using threads and wait needed. Fine. Okay, so this is completely correct, but it doesn't actually show how programs are executing, okay? But let me now show you a little bit more in detail how the lazy programs execute, okay? So let me introduce a concept called lazy suspension. Okay, so when I call, for example, L2 equal times L13, and times is lazy, remember it creates a thread, a thread with wait needed inside. Let me call that a lazy suspension, and let me make a picture. So the L2, which is the result, is actually referring to this lazy suspension, and this lazy suspension is just the call of times L13, which is waiting in a thread, okay? So there's a thread suspended on L2 that contains the body of times L13. So let me write it like this, make a kind of picture. So there's a lazy suspension attached to L2, okay? So when I call this function, all I do is I create a lazy suspension. Okay, so now let's look at Hamming again. So what happens when I run the Hamming program? So the Hamming program is this, this main expression. This is the program on the right here. This H equal 1, this expression, that's the program that's running. So when I call that, I actually create 5 lazy suspensions. Okay? So when I call H equal all that, M1, which is the rest of the list H, will have a lazy suspension, merge T2, M2. Okay? So I've introduced extra variables to show all the lazy suspensions. And T2 has a suspension here, M2 has a suspension here, T3 has a suspension, and T5 has a suspension. So this one, merge T2, M2, okay, it waits on M1, okay? So the merge will only be activated when I need M1. Here, M1, So if I need M1, so I'm asking for the second element now of the Hamming list. So I execute M1.1. This will activate this lazy suspension. What it means is it will execute the body of this merge function. Now when you execute the body of this merge function, let's take a look at the body. This is the merge function. If I execute the body of this, it will do a case on S1, S2. So it needs the first element of S1, and it needs the first element of S2. So that means it will activate these two lazy suspensions. It needs the first element of T2, the first element of M2. So you see, there's kind of recursive activation. I have M1.1, I activate merge T2, M2, and running that will need T2M2, so that activates merge T3, T5, and times H2, and the merge T3, T5, when I run it, it will need the 2 times, and so on. So all 5, so here I have 5 lazy suspensions. All 5 are activated, and they're running, and they will do recursive calls, okay? You see that they're all recursive. The merge will do a recursive call, times will do a recursive call. So when I do a recursive call, I create a new lazy suspension. So basically, when I do M1.1, a lot is happening. A lot of things happen. I activate all 5 lazy suspensions. They all run, and they will create 5 new lazy suspensions when they do their recursive call. So these 5 will disappear, boom, and 5 new ones will be created, boom, like that. A lot of things going on, and all I did was M1.1. Okay, so you see that kind of causes lots of things to happen. Okay, and at the end of all that, M1.1 will be bound to 2 bar M1 prime. M1 prime is a new variable, M1 prime. And then there's these 5 suspensions attached to M1 prime. So the same kind of shape as before, but now from another variable, M1 prime. Okay? Okay. Let's look a little bit more in detail. So I think it's important for you that not to just take the lazy execution for granted, but to understand how the lazy functions are connected together, okay? So let's go a little more in detail here. So I do browse of M1.1. Now remember the M1 here, all these suspensors are attached. So what does this do? Well, this causes merge T2M2 to be activated. What does that mean? It means the body of that merge is executed. So basically I'm just executing the body. So here's the body, okay? It has a case statement. I'm not going to copy the whole thing. It's inside here. I have T2M2, and it's taking 2 arguments, H1, H2, from the 2 T2M2. So this case statement, it needs 2 elements, H1 and H2. So this will activate further lazy suspensions. You see, so the red one, the times H2 will be activated. So this is the one making T2, and the merge T3, T5 will be activated. This is the one, the green one making M2. Okay, so if you go back here, you can see that, or no, maybe here it's better. So when I execute the body here, it will do a case statement, and that will cause this one and this one to be activated. So you see the activations that kind of go upstream to earlier and earlier. So when I activate T2M2, I'm going to activate times H2 and merge T3, T5. And while these 2 are running, this case statement is going to wait, of course. So the red and the green are now activated. So here I continue, let me just continue once here. The red and the green ones are activated. So the red times H2, that means I execute the body. activating a lazy suspension means I execute the body, the function, and this will actually bind T2 to 2 bar another variable, T2 prime, and create a new lazy suspension with the recursive call. And then the other one, the green one, also I execute the body. This activates the 2 times, and so that goes further. I'm not going to go into all detail of the times, but eventually the M2 will be bound to 3, which is the minimum of these 2, and create a new lazy suspension. Okay. And now we go back to this original case in the merge T2 M2. So now we have computed the red and the green ones, okay? Now we can go back to the original case, which was waiting during this whole time. It was waiting for H1, H2. So now the red and the green have run, and so that case can run. So whenever I activate something, I wait here, I need something, I create them, and then I come back, okay? So I've made a picture of that, which you should try to understand, okay? And the arrows show the kind of execution flow. So I start by saying M1.1. This activates this merge, causes this body to execute. This causes times H2 to activate. It causes merge T3, T5 to activate. So the times H2 would eventually bind T2. So there's an arrow going back. The merge T3, T5 will run the body of the merge. This will activate times H3, will eventually bind T3. It activates times T5, will bind T5. And then this body can execute. It binds N2, it will come back here. And then this executes and it binds M1. A lot of stuff happens, huh? In fact, you see that? A lot is happening on that simple thing. So all of that is a consequence of adding one new thing, the weight needed. So this is actually quite a complicated execution flow, huh? You see that? The laziness is not so simple, actually, what's going on. But it's all hidden. You don't actually have to understand it if you run lazy programs. So this is actually the power of laziness, huh? This is a very complicated execution mechanism, but it's still a simple functional program, okay? So this is really the power of laziness, huh? So if I do M1.1 here, you can see, I think you agree with me that lots of stuff happens, and it's kind of complicated, kind of agree maybe with that, that it's not so simple. So there's a lot of power in laziness. All this power is fitting in this functional language, which is pretty neat, isn't it? Isn't it neat? So laziness is one of the real powerful things of functional programming, yeah? And it's still computing the same result. And it's all because of Church-Rousseau. You can see it's very powerful, huh? Okay? So this is something I wanted to show you, that lazy execution does many things in a very simple way. For the programmer, it's very simple, huh? Okay? So lots of stuff happening, huh? And the only thing I do is M1.1. I type 4 characters, M1.1, and all of this happens, and then I can display it here, browse M1.1. All of this is hidden inside the lazy evaluation. Okay, so that's something I wanted to show. So this is something you should understand, because in this course, it's not just programming. You have to understand what's going on. Huh? So you need to understand this. But of course, later, when you make lazy programs, you don't think like this. Huh? A lazy programmer does not think in this way, but it's important to understand that there's lots of stuff going on in an actual lazy execution. Huh? And you can then also see it's important that all of this stuff is based on only one new concept, which is weight needed. So a lot of power can come from one small thing. Huh? See that? So laziness is a major part of functional programming. Huh? And you can see the power here. Huh? Okay. So there I have kind of presented a little bit of the magic of laziness. I have one more example. I won't be able to give it all, where I combine laziness and concurrency. So you see, this program here is not really concurrent program. I'm not creating threads here. Huh? The threads, of course, are used in the semantics of the laziness, but this is not a concurrent program. It's a lazy program, and I'm activating and coming back. There's actually only one thread of control here. Huh? If you look at this diagram here, if you follow the arrows, there's actually only one thread of control. It's actually a sequential execution, lazy. Yeah? It's not concurrent semantically. Yeah? There's only one stream of things happening here, right? Not multiple streams. So laziness is not the same as concurrency. They're two separate things. But you can combine lazy and concurrency. And that gives you even more power. So the deterministic data flow, concurrency, and laziness together. So the final example I want to show is, what does this power give you? So you can see I'm kind of a megalomaniac. Yeah? I'm always talking about power. But this is expressive power. It's that you can do a lot in just a few lines of code. So in order to introduce this final example then will be about lazy and concurrent. So in order to introduce this, let me first recapitulate. So far we have seen 4 ways of doing functional programming. Regular, sequential, but then you can add unbound variables. So sequential with single assignment. So this gives you already some extra power because list functions are tail recursive, so it's much more efficient in terms of memory. Then there's the third one, which is the streams, concurrency. This is what I call deterministic data flow. So threads, data flow, concurrent programming with streams. So you have the producer-consumer streams. And then the fourth one, which I just showed this morning, lazy evaluation, by need with weight needed. So this allows programming with infinite lists and infinite streams also. You can have infinite streams. And then there's a fifth one, where you combine threads and lazy deterministic data flow. So the final example, I want to show you what you can do here. Here I have both lazy and concurrency. What can you do when you have both lazy and concurrency? Okay? So this is the most powerful declarative paradigm we're going to see in this course. It's the most powerful, efficient one. There exists more powerful ones than this. The more powerful one, the typical more powerful one is called constraint programming. But constraint programming is not a general paradigm. It's used for optimizing complex problems. But if you want to see a more powerful one than this, you should follow the courses on constraint programming. Okay, so I'm advertising for my colleagues here. So Pierre Schultz and Yves Deville are actually experts in constraint programming. So that's more powerful than this, but it's not general purpose. It's used for optimization. Okay? This is the most powerful general purpose declarative paradigm I know. So just summarizing, it is confluent, of course, Church-Strasser. It is higher order. Of course, all the paradigms we are talking allow higher order functions. It is concurrent. You can have independent activities that are not synchronized with each other. They run independently of each other. And it has lazy evaluation, so where you run a computation only when its result is needed. So that it has all of that. So then the question, we have all this power, what can we do with it? So I'm going to show you an example that you can program in lazy deterministic data flow, but not in any weaker paradigm, which really uses all this power. Okay? So this example is a very simple idea. It's called a bounded buffer, and it's a concept that's really used a lot in programming. Okay? But if you want to program this in a declarative way, you need both laziness and concurrency. Okay? You can, of course, program it in a non-declarative way, like in Java, but then you have none of the advantages of declarativeness. Then you can have race conditions, and you have to be very, very careful. But here it will be purely functional that I will show you. Okay? So a bounded buffer is actually a very useful concept that's used everywhere in computer systems. There's millions, thousands of buffers in every operating system. So let me first show you the intuition of a bounded buffer. So maybe you have seen already bounded buffers in other courses. I don't know. Have you seen bounded buffer? Not so specifically. Because you can also program bounded buffer in Java, for example. So it's a typical kind of concurrent programming. But then it would not be declarative. So here it's a completely declarative bounded buffer I will show. Okay, so what's the idea of a bounded buffer? So I start with producer-consumer. I'm producing stuff, and I'm reading it, I'm consuming it. Okay? But maybe there's some mismatch between the two. Okay? Maybe the producer is sometimes very slow, sometimes very fast. Sometimes it's very fast in making new things, but sometimes it slows down. And the consumer, sometimes it takes a lot of time to eat one of the things, but sometimes it's very fast. For example, it could be video stream going over the network, where video frames are being passed between producer and consumer. Sometimes they arrive very quickly, sometimes they arrive very slowly, but you want to see them at a constant speed, okay? So the problem is you have lots of variations in speed between producer and consumer. And this can cause bad behavior, okay? So if the producer creates elements too quickly, the consumer cannot use them. So either the producer stops or else it overflows the memory, okay? If the consumer needs a lot of elements very quickly, maybe they're not there yet. The producer is too slow. So the producer and the consumer are kind of mismatched, okay? So sometimes the producer is idling, or maybe you have memory overflows, or maybe the consumer is idling, so you have this kind of mismatch between the two. So the bounded buffer is kind of a component that you stick in the middle, and it solves this problem, okay? It solves the mismatch between the producer and consumer speeds. So you see, the producer and consumer are widely fluctuating and so on. So the bounded buffer will store some elements. So let's say the producer is very fast, but the consumer cannot consume them. So we don't want to slow down this nice, fast producer. So it stores the elements in the bounded buffer, okay? Or let's say the consumer needs a lot of elements very quickly, but the producer cannot produce them. Well, with a little bit of luck, they're already produced in the buffer. So we take them from the buffer. So you see the bounded buffer is smoothing out the variations and reducing the fluctuations between producer and consumer. So when the producer is fast, it puts stuff in the bounded buffer. And when the consumer needs elements very quickly, it takes them from the bounded buffer. So even if the producer is sometimes very slow, it doesn't hurt, or if the consumer is sometimes slow, it doesn't hurt. Okay? This smooths out fluctuations. Okay, now let's see what this looks like in terms of laziness. Okay, let's say we have a lazy producer and a lazy consumer. Okay, The bounded buffer fits in the middle. And the code of the producer and the consumer is not changed. We have identical code. That's actually really nice, huh? We have the producer and the consumer. We don't change the code. We just stick something in the middle, and everything is improved. Okay? So how does it work? Well, there's two viewpoints. Let's say we're sitting at the producer, and we look to the consumer. Well, from the producer point of view, the bounded buffer looks like a consumer. So it's consuming. It looks kind of like a consumer. And from the consumer point of view, when the consumer looks at the bounded buffer, it kind of looks like a producer. Elements are coming out. So the bounded buffer is like two-faced. To the producer, it looks like a consumer, and to the consumer, it looks like a producer. Okay? So the producer and the consumer, they don't see any change when we put this element there. But assume now the system is running and the consumer is not asking. The consumer is very busy and it's slowed down, it's not asking for elements. So that means the producer normally would not produce. But the bounded buffer will ask for elements, will ask for elements, even when the consumer does not ask for them. So it makes sure that it keeps kind of a stock of elements there. Okay? And also in the opposite direction. When the consumer needs elements, but the producer is not producing them, well, the consumer can take them from the bounded buffer. So you see, the bounded buffer is like a storage stock. It stores up elements and it ships them to the consumer in a nice way. And it smooths out the fluctuations. Okay? So what we want to do is we want to write this as a program. So let me just show you what it looks like, but I'm not going to write the code. Okay? So here's producer, consumer. S is the stream. Producer, consumer, and two threads. Well, the bounded buffer is inserted in between. So S1 goes to the producer and S2 goes to the consumer. So what we want to do now is define that. But the bounded buffer will be lazy, but it's also concurrent. Okay? So the goal is to write the code now for the bounded buffer. Okay. And we will do that next week. Okay, so I stop here. So next week, I'll show you how to write a declarative bounded buffer.